So there's a nice new feature in the laminar flow module that has a lot of interesting applications, particularly for problems that involve circulation by a mixer or some kind of an agitator that works like a fan. And in particular, it's right here. If you go to laminar flow interface, the interior fan is what it's called. And if you put that in, you get this feature here. So I made this interior fan, and this works like a fan that you might have in your house to circulate air. And basically, what happens there is it's a blade that rotates and it creates a flow and it creates a pressure drop. So the pressure, we can see it's flowing in this direction. The pressure on this side is higher than the pressure on that side, and there's some flow associated with that. Now, if you prevent the flow from happening, then the pressure drop across the fan increases. And conversely, if you allow flow to go, then there's less of a pressure drop. And so there's a relationship between the flow and the pressure for a fan, just as there is for any kind of a rotating turbine type structure. So centrifugal pumps, for example, have the same kind of thing where there's a relationship between the flow rate and the pressure drop. So what this feature does, it's a boundary condition, although it's an internal boundary. And what this does is it allows you to put in that kind of relationship between a pressure drop and a flow. And in the simplest way, the default is just that it's a linear pressure curve, and we specify the static pressure at no flow. So if flow is prevented, how much pressure drop could this fan make? And if it had all of the flow that it wanted, and so there's really negligible pressure drop, what is the flow that it could create? So those are the two values. And well, you put it in and you get something that will circulate the fluid. So this model is just a box, and I put in a pressure point constraint here. You really always are going to need to have some way to constrain what the pressure is. But other than that, it's all just no flow. And so when we simulate this, we get a circulating flow. This is the velocity, and you can see how it just spins around like that. Okay, so that's pretty good. We can imagine this as a tank where we're circulating the fluid, or a room perhaps with a fan in it, and we're interested in what the circulation pattern is. I added to this a transport analysis, and it's just the transport of diluted species, and all I did was to put in an initial concentration right here. So we have just a little blob of material, and we want to circulate it around and mix it up. And so we can do that with this fan as a mixer. There it goes. It spins around and circulates and spreads out over, I think it's 100 seconds. So just a fairly brief amount of time. And I went in to take a look at what that did, put in some cut points like so, and you plot them up, and you can see the this blob of material circulating around. Here it's coming past, here it's coming past. Each time it comes past, the concentration, the peak concentration is lower, and it's spread out more. So the mixing and dispersion process is taking place, and eventually these would level out to be a constant value. So this is essentially a mixer, and some of you are working on for your projects, working on chemical reactions that take place in some kind of a vessel or structure and need it to be agitated. So this is something that is quite easy to put in, and just want you to keep that in mind that this is an option.